Hello, everyone, and thanks for joining to today's webinar, Automotive Design in Seconds. I'm very pleased to have with me today Tobias Wiegand from Synera, his Customer Success Manager, and Tilman Steininger, who is the Technical Unit Lead at Connected Engineering RLE. As well, we have with us today Nagman Khan, who is the Product Marketing Manager at SimScale. He will be here and join us for the Q&A session towards the end. If you're facing any technical issues, if you cannot hear us or cannot see the presentation, please use the chat to let us know, and we'll try to fix it as soon as possible. And another note before we start, there will be 15 minutes at the end for Q&A, and please feel free to make use of these 15 minutes, ask questions through the questions tab in the webinar software, and we'll make sure to have enough time at the end to answer all your questions. And without further ado, let's start. Quick intro, again, to repeat what the webinar is about today. So RLE International, Synera, and SimScale partner together on a customer project to enable automotive design insights within seconds, right? And we did this with an automated design workflow that was integrated and steered by Synera, the software Synera, and implemented by engineers from RLE, with technology also in the background from SimScale. So basically combining 3 different worlds to actually get a great output. So we will introduce quickly SimScale, then RLE, and look into the project, what this is about, and then have a look into Synera, how it enables engineers to design workflows, robust workflows that make efficient use of the engineer's time. And in the end, we'll demonstrate the final workflow with Synera, SimScale through RLE, and yeah, spend some time in the end for questions and answers. So quickly, for the ones of you which don't know about SimScale, let's have a quick introduction. So SimScale is a cloud-native engineering simulation tool. So we do cloud native means there's no installation required. You can just type in a browser, simscale.com, log in, and run high fidelity engineering simulations. There's a single platform where you can run multiple physics from thermal, electrical, structural, and of course CFD, all in the same unified user interface, which makes it really easy to get started and run the software efficiently. A unique point about SimScale is the embedded collaboration and support features in the software. So you can collaborate with all your colleagues instantly on the same project. Whenever you're facing any issues, we have also live support, in-tool support, so you can share the project with our support engineers, and they can have a look directly into the tool and help you to sort it out. With the power of the cloud, also not only there's no installation required, but also there's a lot of computation power enabled. So with SimScale, you can run hundreds of simulations in parallel. At the same time, you can run basically a full sweep of your design space and run all the simulations in parallel. And you can also drive this design space explorations with an API, so programmatically, as was also used with the workflow with Synera. And then last but not least, SimScale is an AI-enabled tool. Means we have throughout several parts of the software AI technologies that support the engineers in their design workflow. We'll come later to what exactly we mean and at which stages AI technology helps engineers to do their work more efficiently. And yeah, just one example, which will be the main use case of today, is using machine learning or AI to predict simulation results. So in this case, CFD results. What we can do with SimScale, we can run many simulations, hundreds of different variants of similar designs, similar boundary conditions, not exactly the same, but similar. And then we use this data to train an AI model. As with SimScale, all the data is in the same infrastructure, on the same description of the problem. It's inherently made available for AI training, right? There's no translation process needed. There's no cleanup process, no such things that you would have in a more traditional way of enabling AI, where you first need to gather all your data, make it compatible, clean it up, and so forth. And then also the AI models that are then trained directly on SimScale are also delivered on SimScale, and they sit right next to the traditional CFD tools. So you can evaluate when you design with AI, and when you hit a design point that is maybe not very well predicted with the AI tool, you can switch and hit the different button and run it with the full CFD resolution. And the technology that we're using is a graph neural network here in this case, which is powered by our partners Navasto. And with that, I'm handing over to the next speaker, to Tilman. Thanks for having you here, Tilman, and let's hear about the actual project and RLE.
Okay, thank you, Richard, for the introduction and also for the invite to the webinar. I don't want to waste too much time with introduction and talking about RLE and so on, but just a few sentences about myself. So I'm leading the RLE Advanced Engineering Department, which is a part of the Connected Engineering Business Unit, where we are basically responsible for algorithmic development and basically efficiency gaining. So our major topics there are CAE automation and also CAD automation. So I am from my side, from my personal experience, I am now around about 10 years at RLE, mostly responsible for CAE projects, but also from the CAD side. Before RLE, I was at a prototyping company. So basically, I was always a little bit the connection between all these different departments, engineering, CAD design, CAE, validation, but also prototyping. So that basically fits quite good to the connected engineering department right now. So basically, talking about RLE, we are an engineering service provider, around about 2,100 employees worldwide. Our locations are basically related to the huge OEMs. Means we have offices always close to the OEMs. It could be in the US, could be also in Europe, Germany, Poland, also in Spain, UK. 2 or 3 locations in China, 3 also in India, and 1 in Australia. We are basically doing vehicle engineering all over the different fields, like vehicle mechanical engineering, typical one, system engineering, software engineering, and the department I'm part of is the connected engineering. Talking about the project which we did together with SimScale, starting beginning of this year or end of last year, I would say, is basically born out of the topic that we basically have to stay competitive in the future. Means all over the projects we are running, complexity is always rising. Timing is always a point which is basically not that easy to deliver in the timeline which a customer wants to have in the beginning. Performance targets are always rising. Also, development cost is a factor which is gaining and gaining. On the other hand, we have basically always a little resource topic in terms of human resources, but also sometimes on computing capacity, depends on the project. Quality is always a topic, and also budget. Means we have to find ways to stay competitive in the future. And basically, which is a topic all over the automotive market in the moment, reducing the time to market also. And one part of the solution there which we are thinking should be something to basically be one solution in the future, or also right now, I would say, is predict before simulation. Means we should gain efficiency by not use huge CAE loops and predict as much as we can in the beginning. Could also be with experienced resources, experienced employees, which is always not that easy to get in the moment. Means we have to find ways to digitalize these kind of things, and create tools to get rid of that problem in the end. When I'm talking about prediction before simulation, this is basically having faster response from the system. If it is just about having concept validation, or just validation of a design which has to be somehow validated by a CAE department, this is all about having faster response from the system. On the other hand, we have a lot of optimization problems which are becoming more complex and complex right now and also in the future. And therefore, it is important to have as short as possible iteration times. And it depends on the problem you want to optimize, but mainly it is not possible to optimize to the final optimum, because it is just takes too much time to iterate. And this is something we are try to solve this issue with using AI for predict these kind of things in the beginning, and having a much more efficient optimization process. Now coming to a little more technical things. So what we have done in that project was basically, if it comes to vehicle exterior simulation, it is a time-consuming simulation which is necessary for running these CFD analysis for every little change on the vehicle. Means it's basically interesting to see how an AI model could perform and could optimize these kind of workflows. And that was what we was trying in the beginning of this year, or end of last year, to solve with these kind of AI models, and that pipeline basically, which is creating in the beginning synthetic data from a given model, or from a prior simulation deck basically. And therefore, we can run on SimScale a lot of different simulations to train the AI model in the end. And now having an on-premise simulation deck or prediction deck to run fast and efficient optimization loops for example, vehicle exterior CFD analysis, but also, as Richard also was showing, for a lot of other things like, for example, exhaust topics or air duct routing in IP. And we're running two different approaches here. As I already said, we have one on-premise model which we can use directly out of Synera, and we have the other solution of running the cloud-based model on the SimScale platform to use all the computing capacity of SimScale. But maybe to start at the beginning, it always starts with the data ingress and so on. And it is always important to train an AI model to have enough data samples to train the model. And this is something which we solved basically with the Synera workflow to morph geometry and to create more geometry data for having a huge spread of data and CAE samples to train the model in the end. And at that point, I want to hand over to Tobias to show in the beginning how it behaves and how it works to create these kind of geometry loops inside of Synera. So thanks from my side, Tobias.
Thank you, Toman, for these nice words. And also a big thank you to SimScale for having me today. Okay, in the last 10 to 15 years, I worked in various OEM projects around the globe, different OEMs, different tiers, different regions, different products, but all of them had one thing in common. So all the time, the engineers are faced exactly the same challenges. And I extracted, in my eyes, the most relevant ones. So for me, it was always annoying that I spent so much time on repetitive tasks, copying data from one Excel list to the next Excel list, just doing basic calculations, filling out PowerPoint reports. All of these things are not proper engineering tasks in my eyes and keeping me away from this higher value work. So, I mean, I'm a smart guy, so I was thinking about automation. But yeah, I'm a mechanical engineer, not a software engineer. And automating engineering, as engineering is complex, so automating it is pretty hard, especially if you have different tools you want to connect. So your CAD world with your FE world, it's almost impossible for a mechanical engineer. And there was another thing I really don't like. It's every project we started from scratch. So we always went to CATIA, did again the same clicks to create a geometry. Then we went to the FE side. There we created exactly the same clicks to create our FE model. So I was searching for a solution, something like 4 years ago or 5 years ago, and I came across Synera. So I was the first 2 years on the customer side before I had so many wow moments that I decided to join Synera directly. And Synera created a visual low-code language. And with this low-code language, now it's possible, even without any kind of programming skills, to automate my daily work. And it's not only that I can automate it now, I can also do it, the automation super quick. We will see it then in a minute. And how I am doing this, I do it with the process canvas where we have the pre-coded nodes, and I just need to bring this pre-coded nodes in the right order and connect all these nodes. And what I love the most is that I can visualize every single step. And this is also something which is compared if you write a code in Python, is sometimes pretty hard to understand, okay, what exactly the step and does and what is the output. So in Synera, you can visualize the step and see it immediately. And I want to show this to you directly in the software where we will build a workflow. And this workflow is more or less exactly the same what Tillman did. So at the end, our workflow, there will be the engineer will be able to change a parameter of the CAD part, and then everything, or the simulation will run, and we will create a data set for our AI model, which we want to train later on. And if we have built this workflow once, we can then reuse it in the next project on a totally different geometry, as long as it follows the same process. Okay, let's jump into the software. On the right side, we have the viewer where we can visualize geometry, but also the pre and post processing of simulation. On the left hand, we have the canvas where we do the programming without having programming skills. And we do it with this pre-coded nodes. Currently, we have something around 2000. For our workflow, we want to use CATIA. So we first importing a CATIA part. This works also for all these standard other CAD tools as NX, Creo, or Inventor, for example. But not only the part gets imported, it gets also analyzed. So it can read if the designer has defined a parameter. In our case, just the thickness of this pretty simple bracket. And what we can do now is overriding this thickness value, this parameter value. And in the background now, what's happening, CATIA gets opened, the part gets opened, the new value will be inserted, part gets updated, saved, and re-imported to Synera. And you can see it all under 15 seconds, pretty awesome. Okay, in the next step, we will create a simulation model on it, and we will use the color-coded surfaces. Therefore, we have to extract the surfaces. And this color approach is pretty nice because this is now then really geometry independent. If we import the next time a different part, but also has blue colored and green colored surfaces, the workflow will run through. Okay, as we have now the surfaces, we can start to build our FE model, and there we will use our templates. So we have a lot of templates, and we just can import them. In our case, this template uses now our internal measure and internal solver, but you can also connect to other technology. So for example, if you run CFD simulation, then you can connect to SimScale. Okay, and what we have to do now is just replacing the initial stored geometries of this template with our imported values. We will connect the green colored surfaces to the forces and the blue color to the fixed displacement condition, and then the model gets built up, get solved, and we can see the result. So for example, the displacement of the part. And then in the next step, we can also continue here evaluating the result, for example, to extract the maximum value. But we could even continue here going beyond and saying, okay, please automatically create me PowerPoint reports of my simulation result if this is, for example, needed. Okay, as mentioned, Thomas now needs something that he can automatically create thousands of different variants, and that's what we can do with an easy design exploration. So we just link to parameter setup. What are the parameters, and then we can set up this setup more or less. So it is already done. We can already see the minimum and maximum values, and we could also for the responses define if we would have an objective if we want to do an optimization. And then we just open the design exploration, saying, okay, how much designs we want to have. Click on OK, it gets distributed, and we just would need to click on evaluate, run it over the night, run it over the week, depending how long your workflow is running, how much designs you need. And then at the end, you can extract all the values you need to build your AI model. I think, say that, it's the perfect time to hand back the word to you, Tilman.
Thanks, okay. All right. So as Tobias already said, it starts always with the data ingress. So means we have to get the CAD design to the system to predict what we want to predict in the end. Or on the other side, if we want to create data for train the model in the end, we have to do the same again. We have to do variation first and then run a lot of simulations to get the initial model trained as specific as it has to be. So in our case, what we have done here, so just having an easy example for a vehicle which maybe needs some optimization in terms of CFD. Therefore, we created a CATIA model again, and it is an easy transfer again to Synera with all the parameters which are interesting. So, for example, I changed a few easy things on the vehicle, maybe the angle of the windscreen, the angle of the back of the car, a few radii, and so on. So this is something you can now easily change in the workflow itself. Then it took a few seconds to predict and having the information back from the system again. So means the pressure plot or the velocity plot, which is interesting for the vehicle, and also the track value, which is a direct outcome of the prediction. Then you can change a few parameters in the front, for example, a radii in the top or angle of the windscreen, as I already said, and it will directly predict again. You can change a few other things again. And the interesting point at this point now is that you can now run a trade-off study of all the parameters. Means you can do the same thing like Tobias did, running a design exploration or an direct optimization workflow, which is just created by hitting the run button on the screen below. And then it tries all the different aspects on all the different parameter settings of what I did in the beginning. So this is just a little faster to show a little more. You can see the figure up here is now at around about 10 minutes. I don't know how much iterations, I think 45 iterations on that. So it's just, as I said, an example on this. And it is searching for the optimum of that parameter setting. And if you then compare this to the beginning, so this is the initial one with the 0.394 for the initial situation, and then having the optimized one is just again after the prediction, after a few seconds, we are gaining efficiency on the track already after a few iterations by just using a few parameters on the CAD side again. And you can imagine this is just, as I said, an example. You can use that for vehicle exterior simulation, but if you compare that, for example, for a stream in a valve or in an air duct, all the different geometry related parameters like radii, like bending angles, like all the things which could be a direct parameter in a CAD system could be automatically changed by using Synera, and all these different steps are then predicted, and you can run the trade-off study or the optimization directly out of the system on premise. The interesting point after is what is it about accuracy and simulation timing? So for this model, as I was showing right now, the typical simulation, the normal simulation time would be around about 6 hours. For prediction, it is around about 12 seconds. It always depends a little bit on the size of the model and also on the computing capacity. So this is basically on my laptop. The prediction time is around about 12 seconds. The deviation of the model which we was using here is less than 3.4%. In this case, we was using, I'm thinking, around about 70 samples to train the model. It is a little specifically trained on these kind of models, so it depends what vehicle you want to predict in the end. So with the model which we was using here, it wouldn't be possible to predict a smart, for example. But in our opinion, that makes basically sense the most, that basically you know what you want to predict in the beginning of a project. So you have to choose the right model and predict then what you want to predict. And as I said, for round about 70 samples, we have a deviation of smaller than 3.4% of these kind of simulations. So what we are thinking now, using these kind of models for the future and for further project, further topics, as I said, the vehicle exterior simulation is basically one thing which is possible to use these kind of models. Maybe in the end it makes sense to go a little bit more into detail, as I said, for example, the air duct routing in an IP, or also cooling channels in a cooling plate of a battery is also something which we was looking into a little closer. Valve streams also on airfoils, which is an interesting point in here. For an airfoil, it would be directly a multi-objective optimization, because it's always a balancing out of drag and lift. This is also something we was looking into a little closer, a little deeper, because that was also something which we built in Synera to having an optimization loop of airfoils in this case. Also on the maritime sector and also on the rail. Everywhere where it is important to gain efficiency or to gain range, it becomes interesting to use optimization loops and optimization methods to get as efficient as possible for the later on usage for the product. Now, last sentence from my side before I hand over to Richard again. We also created that model together with SimScale, and it is fully placed and fully integrated on the SimScale platform for predicting with the whole calculation power of the SimScale cloud-based solution. Means therefore you can simulate and predict full vehicle 3D CFD simulations also in seconds. I think that makes sense the most if Richard can say a few sentences about that again. Yeah, that's from my side. Thanks to Richard and thanks to Tobias.
Great, thank you, Tilman. Thank you, Toby, for the great overview on the work you did with this project. And yeah, it's really nice to see how you can take this concept and without actually programming something, right? You drag a few items here and there, you get an optimization loop, right? You have the compute capacity in the background, and within seconds you have your optimization set up, right? This is very impressive. I want you to come back now to maybe show here the SimScale side of things. So as Tilman said, the model we saw was 2D. For this specific project, that was sufficient. We did, however, a continuation of the project as well to run a full 3D AI prediction. So in this case, we took, again, like morphed geometries of some baseline car geometries, similar to the Drive AR model. And morph them into different shapes using Synera. And then roughly 70 simulations again, or CAD models were imported to SimScale and run via the API script in the background within 6 hours, right? So each of these simulations had about 12 to 15 million cells. In 6 hours, the whole design study was done, right? And then the AI model was trained on SimScale on the platform, and was also distributed on SimScale. And now you can actually on SimScale set up for another design iteration, the CFD analysis, and evaluate the drag forces, lift forces, and also see the 3D pressure distribution on the car, as well as velocities on the slices and so forth. I'm not presenting this today, mainly because of the thing that you see on the bottom right. So the whole iteration process takes about 50 seconds, right? Which is maybe not exciting for a live demo, but if you compare it to the 5 hours traditional CFD turnaround time, it's a significant improvement, right? So what I wanted to show you instead is that this automotive drag prediction is not the only thing you can do on SimScale with the AI backend, right? So this is, for example, a case for a centrifugal pump, also CFD, but completely different applications where we run about 180 variants. In the end, got a very accurate model of a centrifugal pump. Or structural mechanics, right? Rubber components under different deformation conditions, see how they behave, what is the deformation behavior, what are the stresses, and then evaluate it very quickly with different shapes on the AI model. Or the case which is good for a demo in this case is the muffler, right? So very simple case, a simplified model of a muffler, right? Which we have where we have on the one end an inlet a pressure outlet, and we want to see how the different sizing of the bore holes, the number of holes, the ratio of the bigger versus the smaller chamber, etc., changes the flow distribution and the pressure increase through the muffler, right? And let's have a look how this can be done on the platform. So we see here, this is again in the browser, right? So on SimScale, when you create a new project, you always start with the geometry, right? As we've seen, we can import many different formats: Parasolid, SolidWorks, Autodesk, Rhino, CATIA, all the standard CAD file formats. Once the geometry is uploaded, the next item you do is basically create the simulation setup. So in this case, it's an incompressible CFD analysis. You can see we have a long list of analysis types available. So we start with incompressible, and then quickly add as material air. Then we simply set the boundary conditions for one side velocity inlet. Here on this end, we add a flow rate, a volumetric flow rate of maybe 20 liter per second is more realistic. And then we add the pressure outlet on the other outlet side here on the top. And that's basically it, right? Now we are ready to actually run the simulation. So with another AI model on SimScale, we basically get a prediction of what the duration time would be, right? About 20-25 minutes, and what compute resources this would cost us, right? So in this case, 20 minutes, fine, we run the analysis. Instead, what we could also do, as we have now a set of data trained with an AI model on SimScale, we can simply go here and evaluate it with the muffler demo model, right? So you see we have also here the aerodynamics, the radial pump, and other models. So this is now the muffler model that we want to evaluate. So let's see what we get. It should take about 10 seconds to get a response. Okay, and this is what we get. First of all, it's everything blue, but obviously here we see the surface of the model and the velocity, so it's fine that the velocity is 0. So that's realistic. Let's look at the pressure distribution that we're getting here, right? So with this condition, it says that we're getting about 32 Pascal pressure increase through the model. What is also important that we're getting here is a confidence value back. So that basically tells you how close this new data set is within the training data set, right? So the AI models that we're doing here are only application specific. So if you're going far away from the training data set, the model cannot predict anymore, right? So we can now test this and maybe do, instead of 20 liter, 200 liter, which is far away from realistic ranges and also what is done in the training data. It was only trained up to, I think, 25. So let's see what we get. Okay, in this case, right, we're getting a more or less unrealistic result. But yeah, for the untrained eye, that might not look too unrealistic given that we run high velocities now. But we can also see that the model confidence is pretty low, right? It's actually very low, 0. That means you should not use this model. Instead, right, you can go back and run the traditional analysis, right? You can run a normal simulation. You again get a prediction of the runtime, again about 20 minutes, and you can run now the normal CFD simulation, right? So this is the benefit of having an integrated platform where you have CFD and AI side by side, right? We can not only change the inlet conditions, right, and get a new prediction. What we could also do, let's now predict maybe on 10 liter. What we can also do, obviously, what is probably the most interesting part is changing the geometries, right, and see how different geometries perform, different designs perform under similar conditions. So, and now you simply switch, right? So config 21 unseen to config 24 unseen, you see that's a different number of holes, different hole diameter. We accept this, and again, right, the swapping was successful. It could recognize the same faces, inlet and outlet, and now it does the AI model evaluation. And again, within a couple seconds, we should get a prediction on the pressure and the velocity as well. We can also predict, as we said, scalar quantities, right? The pressure drop could be evaluated here directly, and we see again here now a higher confidence value, 85%, and pressure, yeah, about 7.1 Pascal. And obviously, it's important not only that you get colorful pictures, but also that you can trust the results. So we can check what the actual result in the CFD would have been. And I hope you can see it here side by side, right? So on the right side, that's the traditional CFD solution where we would get 7.25 Pascal. And on our example here, we get 7.1, right? So I think that's an acceptable deviation given that we only waited a couple of seconds for the results for unseen data compared to about 20 minutes for the full CFD. And with that, let's quickly get back to the final words and the final things I wanted to share with you. And by the way, you can use the last few minutes to post more questions. We'll still have 15 minutes at the end to answer all of them. So what we've seen today is basically prediction of CFD results, right? Or structural mechanics or any analysis result, 3D or scalar quantities. But that's only basically a part of the whole process, of the whole engineering design process or the simulation process, right? You start usually with the CAD model, then you have to prepare the CAD, you have to do the simulation setup, mesh, and then run the simulation and then evaluate obviously your results. What we think is, or what we do, this data is on one platform at SimScale, and it can be used to train models for all the different stages, right? What we have today is we have predictions for very simple tasks like the runtime prediction, right? It takes the geometry, the shape of the model, takes the setup conditions and predicts runtime and cost. What we also have is the AI simulation. So it takes the, again, shape of the model, the simulation conditions, and predicts the KPIs, the flow conditions, the 3D results, right? And either transiently in a sense that these are results that are not stored, but also results that are persisted and can be used in optimization loops, where we see at least the same amount of potential is along the whole process. So during the design, right? Once the CAD model is uploaded, it can be identified and CAD preparation suggestion can be made for the user, for example, for the flow volume extraction, right? Which typically happens for a CFD analysis because you design the structure and then you have to do the subtraction to get the flow domain. Or setup suggestions, right? If you upload a model that looks like a pump, the AI, an AI model could tell you maybe use this setup because that is appropriate for a standard pump. And that's currently what we're working on, right? We call it an AI copilot that helps you during your design process to set up a simulation more efficiently. And in the end, right, the goal is to design a better part, right? So you get also support, if you like, to find a more optimal design solution, design alternative. And I think that's also in common with the project that we've seen today, right? So you have different shapes, but you want to find the best under different conditions, and we use AI because it's an easy way to evaluate a large variety of design options, which we always have in such a complex design environment as an automotive. And yeah, with that, I'll hand over to Nagman for the Q&A session. Thanks again, Toby. Thanks, Tillman, for the great presentation so far.
Thank you.
Fantastic. Thanks so much. Thanks so much, Ricard and Tillman and Tobias. Can you hear me, Ricard?
Yes.
Excellent. I mean, what a brilliant presentation by all three of you. Thank you so much for bringing this forward and sharing this publicly with all our attendees. We do have a lot of questions coming in. What I'm going to do is try and group some of these questions together because some of them are quite similar. Okay, so if you don't mind, I'll group 2 or 3 questions together and then I'll pose it to our presenters. Okay. Some of you have asked about the recording of this webinar. Yes, it will be available. Give us a few days to process the video and we'll put it up on our website on simscale.com. If you've registered for this webinar, you'll also receive an email notification with a link to the recording. Okay, let's jump in. Tilman, I guess the first question is for you, right? And the question is, as a customer, as the end user of the software tools, for example, SimScale, Synera, and maybe others, right? You might have other design tools in your stack when it comes to design and engineering. How far along are you in your journey with evaluating and adopting AI? Is what you've shown here the kind of beginning? Have you looked at lots of other tools? What are your kind of early insights into where it's going for Ali?
Yeah, no, there are many things coming up in the moment, and many things which we was looking into a lot deeper. So there are not so many things which I can share in public, so that it's a little difficult always. But for example, we are looking closely into electrical machines also for predict the simulation topics on electrical machines, so the electromagnetic simulation basically, to run again something like optimization loops. So finding the best geometry for example, placing permanent magnets, or how many coils are performing the best, and which torque comes out of which configuration and event. But same for example, we was also looking into a little closer to head impact situations on an interior IP. Which is again something like CAE related development process, which is important to see how which parameter sets in terms of rip height, rip wall thicknesses, overall material behavior, and so on, performs the best for absorbing energy and so on. So
there's a lot going on.
Yeah, sorry. Yeah.
There's a lot going on across different application areas, correct? From everything you're seeing.
It is. So there are many other software solutions out there on the market. We are in the moment pretty interested to see as much as we can, and looking into as much software solutions as we can as an engineering service provider. We have to, but as I was showing together with SimScale and also with Synera, I think that looks quite promising for us in the moment. Yeah.
Amazing, thank you, Tilman. Ricard, the next question is directed more towards you. So you've shown an example, multiple examples of, I guess, flow, right? CFD. Where does the AI features in SimScale, what's the timeline of that applying to other types of analysis? For example, thermal, structural, etc. How's that roadmap looking?
Yeah, so we actually have only shown a subset of the applications that we already enable today. I've shown an example on structural. So we also have structural mechanics enabled for AI prediction. For single body, also multi-body parts. And CHT, so conjugate heat transfer, where you have coupled flow and thermal phenomena, and then use it for AI training. And we will just gradually roll it out across all analysis types and have the full support across the whole SimScale portfolio. I guess somewhere towards mid-end of next year, we are also adding soon some new solvers. I'm not talking too much about that. They will come as well and will be enabled after a while. So the good thing is the methods we're using are mostly agnostic to the physics that we're using. So we don't need to develop much to enable new analysis types, right? We need to just wire it together, but the methods, the base foundation stays the same.
Excellent, thank you, Ricard.
Maybe as a little as a little
Yeah.
outview, the electromagnetic simulation, that was also something we did together, RLE and SimScale, and also Synera, so that maybe this is also something which we can look closer in one of the next months and so on.
Good to hear, Tim, and exactly what the questioner was asking. Tobias, let's come to Synera. So we have a attendee asking, I'll read the question out first, exactly, right? How complicated is the process of integrating different softwares like SimScale with the Synera solution, right? So I guess, and a broader question is, what kind of interest are you seeing from other software providers as well in the CAE market?
Yeah, thank you. So Synera comes with a marketplace where you can find a lot of connectors. This is also available public. There you can already see what's already integrated today. If you search for something which is not integrated, also no issue, because our ecosystem is completely open. So we have a pretty good and pretty well documented API, and you can easily connect every tool as long as it allows to Synera, or it would be even sometimes easier to use some nodes we have in Synera, which we called, for example, run external program. So there are many ways to achieve a connection, and depending on always a little bit what kind of tool you want to connect. But in general, it's not a big deal.
It's quite an accessible tool, right? Depending on what problem you're trying to solve. Great. The next question, I guess it's a generic question, right? I'll pose it to all three of you, the panel, right? And the question is this. Let me reword it slightly. How far away would you say we are from having a multi-parametric analysis with AI for a full vehicle with all the multiple parts involved, including the different types of analysis like aerodynamics, thermal, acoustics, and so on, right? So I guess it's looking ahead, right? In terms of question. And related to that is the step after the AI simulations, right? Between that and the production process, when you actually come to manufacturing the part, that gap, there's still a gap there. So in that gap, you still need to go back. This is correct, to the physics solvers, yes, for before you move to production. Is this accurate way of saying this? So AI is good for early stage disqualification, I guess, of poor design candidates, and you're using it to converge faster on a final solution. Then you go back, use the physics solvers, right? And that's the bit where you can move to manufacturing. So one's a comment, one's a high level question. Maybe Ricard, if you start with your opinion, please.
Okay, yeah, so quick one. Yeah, you should never rely only on an AI prediction to design like a complex part or something potentially dangerous like a car. Obviously, people can get hurt if you make a mistake. So yeah, if you follow the typical design process, validation and qualification procedures. But what AI enables you is to very early, right, to get to a much better baseline design with very little effort, right, and adjust to new constraints quite quickly, right, where people would either need to rely on their experience, right, but maybe there are not so many experienced people on the new physics that we're solving, right? And new automotive designs that are there today, not only electric motors, but also hydrogen and so on. There's not so much experience. So you need something where you can quickly evaluate and test hypotheses, get to a good baseline design. And that's, I think, where AI really plays a crucial role. And to also capture your experience that you've gained over the years, right, in something programmatically, not only in the brains of the people that are your experts, but maybe something that you can hand over to someone else. So this maybe quickly, and then on the full vehicle AI model, I think that's maybe a future dream, but you know, the development has gone so fast with many of the AI solutions that we've seen, right? Just thinking about large language models, they can do stuff that maybe 5 years before no one could have imagined, although maybe experts knew that it was possible. So I wouldn't rule it out. And I think AI is definitely the technology that can make this happen, because it can really enable evaluation of millions of design points in a feasible amount of time and cost.
Tilman can add his thoughts to this, and Tobias.
Yeah, if I would start, so basically it is all this full vehicle AI and so on. It is not just related to just physics and having fast simulation and so on. So it's also about vehicle test planning or sourcing or cost planning, and so there are so many things from different domains coming together, which I would say a full vehicle AI, not sure if it makes sense to 100% think in that direction, but, and this is what I am thinking makes sense the most, is speeding up the process as much as we can. And therefore, I would say AI is the key to solve that topic, to be faster and in iterating, to be faster in development, to get how to say time to market, to reduce the time to market. I think that's the initial thing which we should focus to, and therefore create AI models to, for example, predict crash, predict CFD, predict all the different domains in the end, and maybe in the end bring all these together to one huge model. But I think that's a future vision. Yeah.
Yeah,
Okay,
fantastic. Tobias, any thoughts on this?
Yeah, so builds up a little bit on Tilman's thesis. So I think, or I don't think that there will be this single one AI. We need thousands of smaller AIs, and they need to talk to each other. And I believe all the single challenges we have in this early development phase are already able to be solved by AI today. If you make your homework, if you start to train these models, clean up historical data and all this stuff, this should be already possible today. And then you just need to have a setup where all these AIs can speak to each other. And then with that, you would have this future AI, as Tilman called it. And from my perspective, I think we are already there, that this is possible, but nevertheless, it's a lot of work to generate all these AIs, to train all these AIs. So I will finish with the statement Richard started. So he said something about 5 years, and that's something what I also assume, that in 5 years we will see first OEMs in the market using this kind of prediction to get rid of the first 2 years of the development phase.
Great way to wrap up, Tobias, with a nice prediction there. Thank you so much. I will wrap up the Q&A there and I'll hand back to Ricard for some closing remarks. Thank you.
Thank you, Nagman, for the great moderation. And yeah, thanks Tobias, thanks Tilman for being here today and showing how you work on actual automotive design projects, right, with customers in efficient design environments. And yeah, it was great to go through this project with you, train nice AI models. And yeah, maybe we'll meet together in 5 years again for an update webinar, see where we actually stand 5 years later. Who knows? But yeah, thanks everyone for being here today. You will get the recording as said. If you wish to get in contact with any of us, reach out. You can also reach out to SimScale if you want to get in contact with Tobias or with Tilman. And yeah, if you want to maybe try out the AI models on SimScale, if you have a use case in mind, let us know. We're happy to talk to you and see if there's something we can help you with. And yeah, with that, thanks again for everyone joining, and hopefully see you for the next webinar. Thank you.
Thank you.
Thank you. Bye-bye.
Bye.